Hi, and welcome to Chapter 2 of Network Fundamentals. In this chapter, we're going to start in on our 4-chapter series on media options. This one's going to cover copper core cable. We're going to then move on to fiber optics, wireless, and then transmission options. In Chapter 2, we're going to cover lots of different things about copper core cable. You may know it as coax or twisted pair. These are your options for copper core. So let's get started. It's important to recognize the different types of media that we can use. Remember, media is going to be the devices that we use to actually transmit data around. So it's just a kind of a general term, and there's a lot of different ways that we can define media. The first is a general classification. Either it's going to be a cable-based, or it's going to be wireless. We're going to discuss each one differently. So we'll have a chapter on each of them, but in this case, we're going to start down the cable-based direction, and we're going to start talking about copper core. When we talk about cable-based, we can have either copper core or fiber optic, which is a glass or plastic core as opposed to copper core. Inside of copper core, we'll have coax or twisted pair. We'll describe what those are. And they use an electrical signal sending electrical energy as opposed to light waves or radio, infrared, or microwaves. So we're going to be using electrical energy to send our signals using copper core media. It's important that you have a good image in your head of how signals work. We're going to talk about two different types of signals. First off, we can have what's called an analog signal. An analog signal is a continuous range of values. They work like a wave. So these are analog signals that you're seeing over on the left-hand side. This could be light or radio waves. So just a continuous wave, as opposed to what we call digital signals. Digital signals are discrete values. They are either on or they are off. They are not multiple ranges of values. They are on or off. These are digital. With our digital signal, we can use amplitude modulation, which is where a given height or amplitude refers to a 0 and a different height would equal 1. So different heights, kind of similar to the signals that you see here, where one amplitude is a 0 and one amplitude is a 1. Or we can use our frequency modulation, which is the concept of a frequency being referencing to a 0 or a frequency being referenced to a 1. Different ways. Remember, a digital signal is always either an on or off, as opposed to an analog signal, which is that continuous wave. The word attenuation is going to come up a lot, and I'm going to keep repeating it because I want to make sure that it's a word that you understand. Attenuation is where the signal is going to degrade as it goes along. So it has a loss of its amplitude, and it decreases in its strength as it moves along the cable. We can use something called an amplifier to raise that signal back up. So if you're thinking about digital signals being either a 0 or 1, it's important to recognize that if it gets weaker and weaker, it's going to be harder to recognize, is it turned on or off? We need that amplifier to keep that strong. There is a basic concept of interference or noise. This is an undesired electromagnetic signal. If you have extra signals in your original signal, it's going to make it harder for you to figure out what the signal actually is. So interference can cause problems with your data. If we were looking at it through radio waves, you might think of it as static. It's extra noise that can corrupt or distort your signal. In data, that can change zeros and ones, and it can confuse the signal and things can come across badly. If we take our data and we try to filter it, it can remove those unwanted signals or that unwanted interference. So once it's been applied to filtering, it makes it easier for you to get back to your original signal. There is also a concept called latency. Latency is the amount of time that it takes for your signal to get from the beginning to where it's supposed to go. It's usually measured in hops. So the maximum hops in our latency is what we call our time to live, or our TTL. If the data doesn't get where it goes, where it's supposed to go within that TTL, it just gets dropped. So it's important that that signal is only around for a specific amount of time. It doesn't just stay, especially if it ends up in a loop or some sort of problem in the transmission. It actually just goes, okay, I've been alive long enough. I'm good. I'm dead. It's good. You're going to have to reset it. So we don't end up with a lot of signals that just got confused or didn't get where they were supposed to go. When data is transmitted from point A to point B or one point to another, we call it the bandwidth, which is the measurement of the ability of the network to carry the data. In the sense of, if we have a cable, how much data can that cable carry? So the ability of the network to carry that data. We can use either baseband or broadband. You probably have heard these words, especially referred to cable modems or something like that, broadband modems. Baseband refers to transmitting using the entire bandwidth of the cable. So if you think of the size of the cable, how big is it? How much data can it handle at one point? It uses the whole bandwidth all at once. So it can send a series of signals, essentially a single, but it's only at a single frequency because it can only read one because it's filling that entire band, fills the whole thing. The other is what we call broadband. Broadband can send several analog signals all at the same time because each signal is given its own frequency and it's able to read multiple signals at multiple frequencies and recognize and be able to send those across. So we like broadband. It allows us to send more things through the cable at once. Baseband only sends a single series of signals. Series being signals coming right after each other. A single series of signals is just one list of signals. So the two examples here, there are 3 signals for the broadband as opposed to 1 for the baseband. Trying to remember those. Baseband only has 1 signal, broadband has multiple. When we are trying to communicate between things, we have 3 different options of how to do that. The first is what we call simplex. Simplex is a one-directional transmission. It's going to get you from point A to point B, but point B doesn't send anything back. This is like your TV or a regular website, a static website that doesn't have to go back and forth. So your TV station can send you a simplex communication and it gets to your house and you're fine, but you don't need to tell them anything back in return. A full duplex is both directions simultaneously at the same time. This is like a telephone call. Telephone calls, you hear them, they hear you. There's constantly sending data back and forth between the 2 communication points. There's also the concept of half duplex. Half duplex is both directions get to talk, but only one at a time. So we think of this as the walkie-talkie version. If you have a walkie-talkie, you have to hit call, and then you go ahead and say your thing and you let go. And then the other guy can respond and he can say his piece. But if he's talking, you can't talk on top of him. This is also the basic concept of Ethernet. It runs at a half duplex. So data can move from point A to point B. It can move from point B to back to point A. It just can't move across the cable at the same time. If you have interest in basic electronics, you probably know a lot about DC and AC. But just as a refresher, direct current, DC, flows in a single direction from negative to positive. It always goes the same direction. Alternating current alternates between directions. It goes direct or negative to positive, then it can go positive to negative, and it can alternate between the 2. The opposition or the resistance or the push against direct current is called resistance. It's measured in ohms, and it is longer. The resistance is greater if the conductor is long. So this is where we limit the amount of length of a single cable to given limitations based on the resistance that is going to occur in basic electricity. If you have an alternating current, we call that impedance, and it increases as your frequency increases. It reduces the quality and adds some limitations on your speed because as the frequency increases, you just can't send any more because there's too much impedance against it. When we're looking at the different cables, there is a concept called reflected loss. When the signal reaches the end of the cable, So it gets all the way to the end, and it gets to the end, and then there's a little bit of reflection that occurs once it hits the end and it reflects back. We call that reflected loss. It's the amount of current that comes back, the signal that comes back when it hits the end of the cable. We also talk a lot about crosstalk. Crosstalk is an interference that occurs when the conductors, or the pair, we're going to talk about twisted pair in a minute, when the pair of conductors, they affect another pair of conductors going through the same area. When we talk about twisted pair, we're going to find that there's multiple conductors inside of the cabling. And if there's two of them next to each other, they can actually cause this concept called magnetic induction. Magnetic induction is an electrical phenomenon in which the magnetic field that circles the current that carries the conductor induces a current in a conductor of close proximity. In other words, if you have two cables next to each other, the current that gets created by the data moving through the first cable can affect the cable that's next to it. So in the example here with the different cables, you have a single cable and you've got this magnetic field, which is fine. You add a second cable right next to it, and that magnetic field is across both cables. It's causing a problem by causing this interference in that line. So what we do is we actually twist the pairs. The twisted pairs in example C here is how we can resolve some of the crosstalk, because that twisting area is enough space so that the magnetic induction doesn't hit the other cables. So we'll talk about those different things when we get more into twisted pair. But the concept of crosstalk is just interference, usually inside the same jacket of two conductors next to each other. So a little bit more about crosstalk. There are different ways of measuring and defining what we call crosstalk. The relationship of power between two electrical forces is always measured in decibels. So we can measure each of these different amounts of reflected loss in decibels, just to explain that. We have 4 different types of crosstalk that we talk about. The first is what we call near end. It's on the input side. And it's usually if you have the two cables too close to each other and they aren't twisted enough and you're not able to actually get the data through without having crosstalk. So those are on the near side or the input side. The other option is what we call far end, over on the far side. So having the crosstalk signal be at the far end as opposed to the near end. In the example here that we have of the power connector, we have it connected badly in the second option. So we have the first one, which is properly connected, where the jacket is snapped inside of the plastic connector for the RJ45. In the second one, the wires are exposed. Because they're exposed, you're going to get some crosstalk on that end. So that's how crosstalk gets created. In your equal level far end crosstalk, what we do in this one is we subtract the attenuation from the far end crosstalk, or from the reflected loss that's at the far end. So remember, attenuation is that loss of signal. We can subtract that loss of signal from the far end crosstalk to get an equal level. And we use this in some ways to describe how much crosstalk. The last one is what we call alien crosstalk, which has nothing to do with Roswell. Alien crosstalk is noise that's introduced outside of the jacket, usually if you have a second set of cables going close by. So if you have multiple Cat5 cables all in the same section and they're all right next to each other, if the crosstalk from the first cable is affecting the second, we would call that alien crosstalk, or AXT. So XT for crosstalk, and then we have our acronyms that go along with each of them. Alien crosstalk is much more susceptible at much higher frequencies. It's going to be affecting the cables a little bit more in that point. So when we have our copper core cables, first off, we have a gauge. So gauges, using the American wire gauge rating, is the diameter of the inner conductor. How big is that inner conductor? The diameter of that. And we're going to see a coaxial on the next slide. So you're going to get a visual in that sense. When we create cables, we want to always use cables that are plenum rated. This is the area, the plenum area is the area that is in a building, either underneath a raised floor or above a dropped ceiling. So a lot of cables go running through this area because they're concealed and they're hidden, and that works out beautifully. But if there is a fire, it can leave off some toxic fumes. So when we put the cabling around it, we want to make sure that our cabling is always plenum rated. It's rated for these areas of really close proximity, making sure that it's not going to give off toxic fumes and make us all sick. So as I said at the beginning, two different types of copper core, either coax or twisted pair, coaxial or twisted pair. So we're going to go over each of those individually and explain those. So with our coaxial cable or coax, we have a copper core conductor. It is the core that goes through the middle, and that's what we're using to conduct our electrical pulses. That copper core can choose to either be solid or stranded. A solid copper core is much stiffer, so it's harder to work with, but it's also very cheap. A stranded copper core is much easier to work with. It's more flexible and more pliable. It can also carry more current and have a better quality, but of course, it's also more expensive. When we have our coax, after our copper core, we have something called an insulator or a dielectric. And the insulator is used to help to insulate that copper core from the rest of the cables around it. We then have our foil shield. So we have this foil shield that goes around it and a braided copper shield. So these different shields, again, they help to avoid electromagnetic interference and making sure that everything stays inside the cable as opposed to outside the cable. Finally, after our shield, we have our insulating outer jacket. So that's the black part of the imagery here. And that's the jacket that we put on the outside to make sure that, again, everything stays insulated and included inside. With our coax, we use one of two different types of connectors. Our BNC connector is kind of a circular twist type connector. You push them together and then you twist it to lock it in place. And the other is probably what you've seen if you had cable TV 10, 20 years ago, which we call an F-type connector. And it's got the little copper core sticking out, and then it's got the little connector, and you push it into the female end and screw them tight. So that helps that connector. So this is your basic coax. Couple of different types of coax that we use. Now, a couple of them are listed here that we don't actually talk too much about, but the big ones to remember are always going to be your RG6, which is what we still use for cable TV, your RG8, which is called thick net, which is usually used for backbones. It's a little bit harder to work with, but it does have a length of about 500 meters, which is really convenient. So this will be your Ethernet networks or your backbones. And then there's the RG58, which we call thin net because it has a thinner diameter. It's easier to work with and more malleable than the RG8, but it's just not used as often anymore. So again, it can also be used for your backbone. So the RG11, 59, and 62 are also different types. You can see what their common name would be, either the CATV or the thick core. And then they're different impedance, the amount of resistance that you're going to have in those situations, the different diameter sizes for those, and then a basic description. So these are going to help you. A lot of cable and satellite TV still use coax, but a lot of times when we get into Ethernets and networks that we're going to be using twisted pair. So let's talk about that one. Your twisted pair cabling is generally what we call CAT. So either a CAT 4, CAT 5, CAT 6, CAT 7, different types of categories for the different types of twisted pair. After category 1, which was used way back at the beginning, originally for phone systems, which only used 2 of the 4 twisted pairs anyway. So when you had a phone system, you only needed 2. But with our data, we usually use 4 pairs of twisted conductors. Each of the conductors is given a color: orange, green, blue, and brown. Sometimes the brown is gray, sometimes the brown is white, sometimes the brown is somewhere in the middle. But the others are usually orange, green, and blue. These are 2 conductors, so 4 pairs, and they're twisted together. Remember how we talked about that twisting and that crosstalk, making sure that they're twisted. When you have these, you can have either shielded or unshielded, and we refer to them as UTP, unshielded twisted pair, or shielded twisted pair. Your shielded protects you a little bit more from crosstalk and interference. So we like our shielded, but of course it's a little bit more expensive. When you're looking at your twisted pair, we use an RJ45, as I've mentioned before, the connector, and we're going to talk about how to put together a twisted pair and connect it in a couple of slides. The Cat 6 and the Cat 7, or the Cat 6E and the Cat 6A are a little bit different, and there's a description in your book, and I would recommend you look into it. The A is an augmented version of Cat 6, whereas Cat 6E actually technically exceeds its standards. Cat 6 was also where we introduced a plastic core in the middle of our cabling to add some extra strength. So Cat 5 didn't have that plastic core, but Cat 6 does. And you can see how each of these 4 pairs, or 8 total twisted conductors, build up to create our Cat cabling. Each of the different categories, starting with category 3, offers you either unshielded or shielded, all the way up to Cat 8, which is only available in shielded. Each of them has a different frequency rating. So what are they rated for is their max frequency, and what is their different data rates. As you can see, both Cat 5 and Cat 5A, or E, excuse me, both offer between 100 and 1,000 millibits per second while using all 4 pairs. The Cat 5 was commonly used for 10 base T cabling in a lot of networks, but we've really moved a lot up to that Cat 6 if given the choice, if we have the money. Cat 6, of course, has a maximum frequency a little bit higher and can also have a data rate up to 1 gigabit. So you can see that we're calling them different categories, and you're seeing how many pairs and their frequency rating. Let's look at the 802.3 classifications. So remember how I said that IEEE was going to come in a lot, and we're going to talk about that? So they have the 802 specifications, and in this case, the 802.3 is our Ethernet classifications. These are different ways of classifying our Ethernet cables. So it's important to recognize the different classifications and the different cables that they reference, because in your Network Plus test, it's going to expect you to know these. It's important for you to recognize as well both the maximum and the minimum segment lengths on the different cables. Some cables can be longer than others. And if you tried to put in a shorter or a longer cable in a place where it's not allowed, it's going to give you some trouble. One of the things that we can add at the end of our segment of cabling is what we call a terminating resistor. This resistor is there to absorb the signals that are at the end of the segment to try to avoid that crosstalk that comes back from different ends, and just to absorb your signals. When we talk about the different categories and classifications, we have our basic 10 millibit category, and this is going to be either your RG58 or your RG8. Remember, we talked about those, the thin net and the thick net, these two, or basic category 3, 4, and 5. These can all be in this 10 base classification. When we talk about our classifications, it's important to recognize what the different segments of it are. So a 10 base 2 references a data rate of 10 milliseconds. That's what the 10 refers to. Base refers to it being baseband as opposed to broadband. And our approximate maximum segment length of 2. In this case, the 2 refers to 200, not 2 meters, but 200 meters. It's actually 185, but it's close to 2, so we're good with that. So our 10 base 5 is going to give us data rate of 10, baseband, and an approximate length of 500 meters for our maximum. When we get to a 10 base T, this is going to be a twisted pair. So instead of it referring to the length at this point, now it's referring to the media type. So the T refers to twisted pair. So a 10 base T is a 10 millibit per second baseband twisted pair. So again, Cat 3, 4, and 5. After our 10 millibit category, we have our fast Ethernet. These go at 100 millibits per second, so they would be a 100 base T. In this case, we can have a T4 or a TX. and the X can refer to which 8023 category we're going to be using. Yes, that last section is not consistent and it can make it very confusing. So it's important for you to take some time to look over the chart and see if you can understand how the name turns into the shortened version or the abbreviation. So the 100 base CX, which is also a fast Ethernet. And then, of course, we have our 10 gigabit as well. So we have our gigabit Ethernet and our 10 gigabit Ethernet. And these are different options that we have for our category classifications. Again, this classification is an IEEE 8023 classification, as opposed to being referred to as those categories. But you can kind of see how they correspond. You've got your Cat 5, your Cat 6, and how it corresponds back to your 10 gigabit Ethernet. When you are looking at your network, you have a couple of hubs and you have a couple of computers together, you need to be careful with your 10 base T cabling. Any cable on the network should not exceed 100 meters. Think of that 100 meters as a hard and fast rule. Do not make any segment more than 100 meters because it's going to cause trouble and problems with your cabling. At the same time, there is also a minimum segment length of 0.6 meters. Remember, a meter is roughly 3 feet, so 0.6 is roughly 2 feet. You need to make sure that you don't have any cables that are less than 2 feet, because that's your minimum cable length. If it's any closer than that, it's just too close between the start and the end, and it's just not going to work nicely. So for cabling, we have a minimum and a maximum length. And this graph is just going to show you your maximums, your minimums in meters of how much your each segment should be. So when we're talking about our IEEE 8023, we need to talk about how they are going to access their media. How are they getting data into the cabling? Okay. This cabling is going to use what we call CSMA. So CSMA stands for Carrier Sense Multiple Access. We also have the option of either having collision detection or collision avoidance. So let's break down each of these words and make sure we understand what they mean. The carrier sense means that your network card is actually able to recognize data being transmitted. So it's going to be able to look at the different data that's being transmitted, and it knows what's being transmitted. So the carrier has some sense of that. The multiple access means that the cabling itself provides access to all of the network cards that are connected on that cable. So it's going to allow the network card to be able to recognize, is there any data going through the cable right now? Kind of like if you're on a street, being able to see whether there's traffic. Okay. At this point, we have two options. We have collision detection or collision avoidance. With collision detection, CD, the NIC can actually detect if a collision has occurred. So we threw some data out on the media and it bumped into something and it caused problems. So that data never got where it was supposed to go. It knows that it happened. So it knows that the accident occurred and it will go ahead and resend the data. That's detection. Avoidance is where the NIC is actually going to look at the traffic to try to avoid a collision in the first place. It doesn't respond to a collision when it occurs. It simply tries to avoid the collision in the first place. So what it does is it waits. So it's kind of like waiting for traffic. You're trying to make a right-hand turn. You can't make a right-hand turn until all the traffic is gone. Once it's gone, we're going to wait just a second, make sure we're clear, and then I'll go out and put myself on the media and allow things to work. The problem with collision detection was that even though the workstation actually keeps an eye on the traffic and only tries to proceed if there's a break, if another station tries to send traffic at the same time as the first one, they both send traffic at the same time and they can cause a collision. So being able to add that brief lull or that brief waiting period once you see a break will allow you to avoid collisions. So we've moved a lot of media onto the CSMA with the collision avoidance rather than the collision detection. We're going to talk a little bit more about this CSMA CD versus CA as we get into other media as well. When you go to build your CAT cabling, So in this case, I think we've got a Cat 5. We're going to be designing different wiring options and connections. First off, remember the RJ45 is the name of the little plastic thing at the end, the adapter that we're going to be using. Each of those different 8 cables, remember there are 4 pairs, so 8 cables, follow a specific order for their specification. We have 2 that we refer to is the 568A and the 568B. 568A starts with the 2 green ones. It then takes the stranded orange, the 2 blue, and then the solid orange, and then adds the 2 brown on the side, or the gray, or whichever side. So the greens and the oranges. With the 568B, the greens and the oranges are switched in position. So you can see in the second view here where the green and the oranges switch between the 568A and the 568B. It is important for you to recognize which cable your cable is designed as if you need to splice it and rebuild it. So if you need to cut your cable in half and put a new port on the end of it, you need to know what it was on one side so that you can set it up correctly. Different situations use the 568A and B separately, so it's important to recognize you can't be guaranteed that your cabling is going to be a 568A or B. You need to actually look at it. Another name we use for the RJ45 is the 8P8C because there are 8 pairs or 8 conductors, or 8 pins and 8 conductors. So the 8 pin, because there's 8 pin points and there's 8 conductors that are going to connect to it. When we want to make a straight through cable, this is where a cable just takes from one side to the other and all of everything's straight. All of the pins match. So if I have a 568A and I need the other end to also look like a 568A with nothing switched. We can also create what is called a crossover cable. A crossover cable is where 2 of the pairs are cross-connected. We're going to look at what that looks like in a minute. But it allowed you to actually take the receiving end from one computer and have it as the input in the other computer and vice versa, so that you were able to hook 2 computers together directly. With an auto-MIDIX, which is a medium-dependent interface crossover, it eliminated the need for the crossover cable because it actually resolved that for us. If it was a straight-through cable and needed to be a crossover cable, it would do it automatically. When we're talking about data that's going through, we are going to talk about the maximum transmission unit, or the largest amount of data that can be sent at any one time. So if we have data that we want to send, there's an actual limit to how much data we can send. Another type of cable that we use is called the rollover cable, where each of the cable pairs is completely reversed. So none of the pins are in the same position. They are all switched. We also have a power over Ethernet cable that actually provides power through your Ethernet cable. And this is used in a lot of situations where you can take your Ethernet and plug it into something and receive power through your Ethernet through one of the twisted pairs. So you can see the 2 examples here I have of a straight through cable where the 1 corresponds to the 1, the 2 corresponds to the 2, vice versa, and a crossover cable where our 1 is going to go down to our 3 and our 2 is going to go down to our 6. So we've crossed them over, so they're in different positions. When we are going to install our RJ45, so we need to attach this connector at the end. If you do not choose to do the lab for this assignment, I recommend highly go find a YouTube video and watch it. It's really important for you to actually get your hands on a cable and snap them and actually put together your 45 connector. I know that some people are taking this class online, and so you can't get into the lab and you may not have access to these tools. They're not that expensive, by the way, if you want to just run down to your Home Depot and pick some up. We have the plastic housing that holds the RJ45 connector. And then, of course, our cable. In this case, we have a UTP cable, so an unshielded twisted pair cable. It has the 4 conductor pairs, and it has its jacket. When we take our little crimping tool and snip them in there, you have to make sure that all of the pins are in exactly that right position, the 568A or 568B, depending on which one you're going to do. So the way we install it, you strip the cable, expose the pairs, untwist the pairs to get each of the 8 cables correctly, put them all in a line to get them in their designated pin area, and then use the crimp tool to clamp the end of the cable. Make sure when you clamp it that your jacket is inside the clamp. Otherwise, you get that crosstalk. One of the standards that we reference is the 802.5, which is a token ring standard for its network. Now, we talked about ring topologies. This is a ring topology, but it uses a multiple access unit to make that ring. Even though it looks like a star, inside of our multiple access unit, or a MAU, it has a token passing access, so it goes around in a circle. And you can see if something is plugged into the MAU, it goes around and then it goes down into that network and back, or that computer, and then back up. And it does this as long as it is in any individual port. If it is not in the port, it just goes straight through. So this allows data to be in a continuous loop. This can be used with either UDP, STP, so unshielded, shielded, or any specific proprietary cable. When we create our wiring, it's important to be able to recognize the different pairs and the different problems that we can create with that wiring. The first is what we call a short. If you have a short, you have two cables, two conductors that are just not connected correctly. If they touch each other, it will shorten the loop, shorten the circuit, because instead of continuing on to the end and then coming back, it'll stop there and shorten it. So we call it a short. We also have the option of an open, which is simply a break in the cable. There's a hole in the cable. That's not good. And we can ground our cables. So if any of those conductors are actually in connection with the earth, so if the jacket's torn and it's touching dirt, or it's touching ground, or it's grounded, that will also cause problems with the electrical circuits running through them. The four examples here are the reversed pair, the crossed pair, a split pair, and then of course the normal style. So in our normal, up at the top is our normal connected cable, saying that everything is connected fine. One is connected to one, two is connected to two, and everything is lovely. In our second one, we have what's called a reversed pair. You can see one of the pairs is reversed. In our third one, we have our crossed pairs, where the two pairs go down and the other two pairs come up and they actually cross each other. And then the fourth is what we call a split pair. So one of the pair from one side is in the position where another pair from a separate, another conductor from a separate pair is connected. This is going to be really important also in your homework. So we're going to reference these different things. I hope that that kind of makes sense in the different ways that you can have reversed pairs, cross pairs, or split pairs, different ways of incorrectly wiring your cables. Now, if you meant to make a crossed pair, then that's fine. But if you intended it for it to be straight through and it isn't, this is what's going to happen. There is an item called a cable tester. So you have a cable tester and you attach both ends of the cable and it'll tell you if the cables are designed correctly. Okay, so the assignments that I recommend for this chapter. We're going to do the review questions, obviously 1 through 26. In the study guide, there's a PDF document, obviously, and there's 18 different sections. Some of them are just repeating the charts and the graphs from the book so that you get kind of a view of what those maximum lengths are, what the different data rates are, how you can have different types of wiring. Make sure that you really understand those. When you get to the lab activities, so 5, 6, 7, 8, and 10 should be able to be just fine on your home computer as long as you're connected to the internet. If you need to do 3 and 4, you need to have a cable with a crimper to build your cable and then to create your crossover cable. That crossover cable is used in lab 9. So we're doing labs 3 through 10. 9 is optional if you do not have a secondary computer or you can't get into the lab. It's going to be really hard for you to do lab 9. If you don't have access to a crimper and a cable, it's going to be hard for you to actually do 3 and 4. So I recommend for 3 and 4, if you can't do them, go find a YouTube video that walks you through how to make those cables, at least to kind of get that visual in your head. And if you can't do 9, just let me know that you couldn't do 9. I've again put in a study mate for chapter 2 and your chapter 2 quiz. Remember, no notes or books. Get used to it. The worst thing is for you to do all of these quizzes and have your books and your notes right in front of you. And then when you go to take the Network Plus exam, you don't know how to live without your notes. So hopefully that was a good start into cables and copper core cables. Come back next time for chapter 3, where we'll get into fiber optics. Have a great week.